Hello and welcome to the first beat in the life of Outliers. The Outliers is a team of experienced engineers in industry with a combined experience of 24 years. Our first season will revolve around the role of thermodynamics in our daily life, where we will attempt to bridge everything students and engineers see in textbooks and industry. In our first episode, I'm going to touch down on definition of the first three laws of thermodynamics, namely zeroth, first, and second law of thermodynamics, energy's role in human civilization, and why energy density matters. Then we'll move to the most exciting part of studying thermodynamics, as well as all undergrad knows, which is cycles, and where we can see it in industry and even in our own bodies. Then how that cycle varies as a function of space-time, which brings us to steady versus transient systems. And last but not least, the concept of degree of freedom and how the more we make choices, the more we constrain the outcome, which eventually end up totally dependent on those choices. Laws of thermodynamics are literally nature's auditor for saying what can and cannot happen. That's where every single idea, device, or a process needs to meet its first test, whether it's approved to pass or not. Like, for example, I cannot be working on studying kinetics of chemical reaction, where the conditions are already at equilibrium. Thermodynamics is the first milestone for engineers, and we must validate it before moving to the next step. Zeroth law is pretty simple and straightforward. If two bodies in contact have the same temperature or have been in contact for a very long time, then they are in thermal equilibrium. So here you go, one law down, three to go. The first law of thermodynamics stresses that the total energy in any form, including its condensed form, which is mass, is conserved. The sun started with initial mass and energy, and throughout its life to date has been transferring mass into energy through hydrogen fusion. Living organisms like plants use that energy, which we call sunlight, to produce carbohydrates as energy source for their survival, and oxygen we breathe. Plants and animals end up being fossilized and turning into hydrocarbons that we use to propel our rockets into space. That's what the first law of thermodynamics is. It's a cycle of energy transformation across space-time. Despite being super intuitive, the second law of thermodynamics, also known as the entropy law, is often a point of confusion because we don't normally talk about quantities of entropy in our daily conversation or on the news like we would normally do with energy. And I think that's where the repulsion from thermodynamics seems to stem. But every time we see a clip with a cracked egg get uncracked, spilled milk getting back to its container, we instantly know that clip is being played backward in time. And that's pretty much the core connection between our minds and the second law. Another perfect example, if we decide to be buying a car or a fridge, the first thing that comes to our minds is that how much gas mileage this car has or how efficient this fridge is. That's a question that only makes sense when we talk about second law, not the first law. Because only in the second law of thermodynamics do we learn that the different forms of energy aren't created equal. Hence, second law. Matter, energy, and entropy are all physical quantities that move through space-time. When they are fixed in time and move through space, that system is in steady state. Meanwhile, once time component is added to that mix, the system becomes transient. Steady-state systems are like a power plant with a consistent load output, or a car with internal combustion engine, where energy demand is always matching the energy supply. Transient systems are like a brewery that makes a couple of batches at a time, so we would find there is a sequence of steps happening in series as a batch preparation, charging, heating up, cooling down, etc. Transient systems tend to be practical in small scales, more wasteful, but are not as complex as a steady-state system, relatively speaking. Steady-state systems tend to be more sustainable over long periods of time or distances, but tend to be more complex. With first and second law, in addition to the steady versus transient system definitions, we now have the bread and butter for defining a thermodynamic cycle. A cycle, as the name implies, dictates that the start and the end points are the same. We start from a point that we eventually get back to through a series of steps that involves an exchange of one form of energy into another form, while fulfilling both laws of thermodynamics. Thermodynamic cycles are divided into two types. A power cycle, which is, as the name implies, will extract mechanical energy from an energy source. For instance, a power plant where fuel is fed to make steam that turns a turbine to make electricity or drive a compressor. A heat pump cycle is like a fridge or air conditioner at our homes. The objective of such cycle is to be moving heat from low to high temperature levels that otherwise won't spontaneously occur. Now, combining our knowledge, a steady transient system and a power cycle. A power cycle could be either different steps or processes happening in the same equipment at different times, or same steps within different equipments happening at the same time. And to give a brief comparisons for those, the Otto cycle, for example, is an internal combustion engine, is a transient power cycle. All steps happen in one place at different times. Fuel addition followed by ignition, then piston expansion and combustion products released. Then we go back to step one. Transient cycles tend to have the energy carrier as the working fluid and are compact, having cyclical temperature and mechanical swings. On the other hand, a Rankine cycle, like a power plant, has different pieces of equipment, like a boiler, steam turbine, and a water pump, where conditions are always fixed, and hence the overall cycle is fixed in time. Steady-state power cycles tend to have different systems for the energy source and working fluid, and have more equipment but consistent temperature and mechanical loads. And that's one of the reasons continuous steady-state systems have the upper hand over transient cycles. Before we close out, we need to touch down on two topics. The first topic is about a core principle of thermodynamics that we are very familiar with in our daily life. From project executions to voting in elections, we know we start off with a freedom to pick a given set of choices, and we have to live with the output or the result of these choices. An athlete can either choose to go through training regimen and become stronger, or avoid the training for short-term peace of mind and stay at the same performance level. The athlete can only pick one scenario and deal with the consequences that choice entails, but cannot choose to be stronger without training, for example. Similarly, in thermodynamics, as we will see in our subsequent discussions, Gibbs found out that a system defines how many state functions can be specified to constrain it, based upon the number of phases, components, and chemical reactions taking place within the system. A simple example is a single component working fluid. If I have only one phase, I will need to be defining two state variables to get my coordinates fixed on that map. If I have two phases, I will only need to make one choice to fix the system. Okay, so what happens when I have three phases coexistence? How many choices left for me? Well, you can't make a choice, because we all know a triple point is affixed for a given single component. The more specifications the system has, the less choices are left for us to make. The second topic is the energy density, as becoming critically essential during our times. Globally, companies are competing to find a sustainable alternative to fossil fuels. However, a viable alternative has to meet three conditions.